a video working through Ellipse Day 1 notes for Algebra 2 Pre-AP. If you have this worksheet, you got it hopefully already in class today, and if not, if you can't find yours, you can get it off of the online calendar on my website. You're more than welcome to print that off and make the notes that I make on here as we go. Okay, so we have an ellipse, which is our next conic section that we are going to study. We've had circles, but now we're going to do ellipses. So we've got the set definition and the conic definition, just like we had before. For the set definition, an ellipse is the set of all points x and y in a plane such that the sum of the distances between x, y, and two fixed points called the foci is a constant. Or we have a conic definition, which is an ellipse is a closed curve formed by the intersection of a double napped cone in a plane that is not parallel or perpendicular to the axis of the cone. So you do need to know both of those definitions. Okay, so we've got two different versions of an ellipse here. We've got this horizontal one, and we've got the vertical. And on this whole notes page, the horizontal information will always be on the left-hand side and the vertical on the right-hand side. You'll notice these two things are really the same thing. Everything's labeled in the same way. It's just that this first one has been turned on its side, and so now it's standing up right here. So for this horizontal ellipse, we've got a center right here in the middle, and then going out to the left and the right, we've got the vertex. And the major axis will connect these two vertices. It's the whole thing all the way across. And the major axis is going left to right here, but the minor axis is going top to bottom, and it's smaller. So the major axis is always bigger than the minor axis. The major axis connects the vertices, and it will also contain the foci. And then the minor axis at the endpoints will be the co-vertices. Same thing over here. So you see this vertical ellipse. This time, the major axis, this longer one, is going vertically, and it connects the vertices. And the foci are also on the major axis, and the minor axis is going left to right, and at the endpoints we've got the co-vertices. So let's look at their equations. Okay, so I've got the standard or graphing form of the equation of an ellipse. So for this horizontal ellipse, I've got x squared over a squared plus y squared over b squared equals 1. Well, this will be true if we have a center at 0, 0. But remember when we were looking at circles, whenever we subtracted something after the x or the y, that would make the center of the circle. It's the same thing for the ellipse. So here the center would be at hk, so it has the opposite sign. And then for a horizontal ellipse, this will be divided by a squared, and a squared and b squared, those have to do with the major axis and the minor axis. So up here on this picture, let's go ahead and label a couple of things. So this a right here, that's actually always going to be half of the major axis. So going from the center over to one of the vertices, it doesn't matter which one, but that would be a. For the minor axis, half of that is going to be b. It's going to be b. So a is half of the major axis, b is half of the minor axis, and then we have c, and that's going to be the distance from the center to one of the foci. And that's true for either one. So over here from the center to the foci, that would be c. Going from the center to a vertex, that would be a. And then going from the center to a co-vertex, that would be b. So it doesn't matter which way it's standing. A, b, and c always represent the same things. So for this horizontal ellipse, we have x minus h squared over a squared, and then plus y minus k squared over b squared, where the center is at hk. But a squared, the fact that it's under the x tells us that this is going to be horizontal. Whereas for vertical, it's almost the same setup, except underneath the x we have the b squared, and underneath the y we have the a squared. So the a squared and the b squared switched. So if you're looking at an equation and this had been filled in with numbers, how do you figure out if it's horizontal or vertical? Well, you just have to look for the bigger number. So if the a squared, if the bigger number is first, that's the a squared, so that would mean it's horizontal. But if the bigger number is second, so b squared, the smaller number is first, and then you have a bigger number here second, then that would mean it's vertical. Otherwise, the equations are the same. A squared is always greater than b squared in ellipse, and remember that's because a squared, or a, is half of the major axis, and the major axis is always going to be the longer axis. So it makes sense that a squared is always greater than b squared in an ellipse. Let's keep going. Next on your notes, you'll have all these words, and I don't really want to sit here and read through all of them. You can pause the video or read it off of your notes. This is really just what we did to label the two equations in the graphs up there, just in word form. And then this tells you how you can find the vertices, co-vertices, foci of an ellipse based off of the equation. And so for the vertices, if you have, and just again, everything on the left-hand side is going to be for the horizontal, and then everything on the right-hand side is vertical. And then also the center at 0, 0, that applies for all of these that are on that column. So there's really like 4 columns running down here. Okay, so if you have a center at 0, 0, the vertices would be plus or minus a comma 0. Co-vertices would be 0 plus or minus b, and the foci would be plus or minus c comma 0. And you can read through the rest of this as well. I think this makes a lot more sense when we get to the examples, and I'll show you how to do that in just a moment. But one important thing here is the foci of an ellipse. If you know a squared and b squared, or a and b, and you don't know what c is, you see this formula looks a whole lot like the Pythagorean theorem, except there's a minus here instead of a plus sign. So c you could solve for by taking a squared minus b squared and then taking the square root, and then you would have c. So you can find the foci if you know a and b, or a squared and b squared. And then the vertices and co-vertices, again, a is half of the major, or the major axis is 2 times a, minor is 2 times b, same thing. And then finally at the bottom of that first page, for the lines of symmetry, these are just the lines that divide the ellipse in half. So you'll always have 2, a vertical and a horizontal. And so your lines of symmetry will always be x equals the x value of your vertex and y equals the y value of your, not vertex, center. X equals the x value of the center and y equals the y value of the center, k. We also have the eccentricity of an ellipse, which is just telling you how much this ellipse is being stretched as far as how it is related to a circle. And the formula for that will be c divided by a. So since c is less than a in an ellipse, remember c would be from the center to a foci, but a would be from the center all the way past the foci out to the vertex. So c is always going to be less than a in an ellipse. So e, the eccentricity, will always be between 0 and 1. An eccentricity closer to 1 makes it more elongated, and closer to 0 makes the shape more circular. So let's look at a couple of examples. Okay, so in this first example we have x squared over 16 plus y squared over 25 equals 1. So the center is going to be at, well, we look at what's added or subtracted after the x and y, and there's nothing there, so that means the center is going to be at 0, 0. Then to figure out a and b, we'll have to look at the 16 and 25, and first of all figure out which one is bigger. Well, 25 is a bigger number, so that means this one is the a squared. So 25 is a squared, so a is 5. Well, if 25 was the a squared, then the 16 is the b squared. So if b squared is 16, then the square root of that would be b is 4. To figure out c, remember we use that formula, c squared equals a squared minus b squared. So if a squared is 25 and b squared is 16, c squared is 9. Therefore, c would be 3. Now let's go ahead and graph these points. So we have a center at 0, 0. Because the b squared was first, that means this is going to be a vertical ellipse. So it'll be taller than it is wide. So because of that, we're going to start at the center, and we'll go up and down for the direction of a. So we'll go up 1, 2, 3, 4, 5, and we'll go down 1, 2, 3, 4, 5. B will be going left and right, the different direction from the A, so we'll go to the left and right 1, 2, 3, 4. 1, 2, 3, 4. And then there's C. It always goes in the same direction as A, so I'll count up and down 1, 2, 3, and 1, 2, 3. So So I don't connect anything with the foci or the center, but I do connect the vertices, co-vertices together. Maybe you can draw a better ellipse than me. Okay, so this was the ellipse, and it was vertical because that b squared term was first. So let's scroll down a little bit. Okay, so for the vertices, remember those are the endpoints of the major axis, the longer axis. So the vertices are at 0, 5, and at 0, -5. The co-vertices are the endpoints of the minor axis, so that's the shorter axis here. So we'll have -4, 0, and +4, 0. The foci are those other 2 points in there, so we have 0, 3, and 0, -3. The length of the major axis, so going from vertex to vertex, that would be 10. You could also know that by taking 2 times A. 2 times A is always the major axis. The minor axis is always 2 times B. And B here was 4, so this is 8. Or you could look up here and count 8 across from left to right between the co-vertices. E is that formula C over A. Well, C was 3 and A was 5. So then that is in decimal form 0.6. So it's a little more than halfway between 0 and 1. So it's a little more elliptical than it is circular. And then for the lines of symmetry, those are just going to be our 2 axes of symmetry. So we have x equals 0 and y equals 0. So the vertical and horizontal lines that went through the ellipse. Let's look at another example. We have x plus 4 squared over 9 plus y minus 3 squared over 4 equals 1. Okay, so the center, we look at what's behind the x and the y and take the opposite sign. So the center is at -4, 3. And then we look at the denominators here. We have a 9 and a 4. So we look for the bigger number. There's the 9. That means the 9 is the a squared. And the a would be the b squared. So a here is 3. B here is 2. So then for c, again, we use that formula. C squared is a squared minus b squared. So c squared here is 9 minus 4. So c squared equals 5. So c is the square root of 5. And you can leave it like that. However, it's more helpful whenever you're graphing it if you know what the decimal form is. And that's about 2.24. And that's easier to count to get to the foci to me than it is the square root of 5. So let's start graphing this. We have the point -4, 3. 1, 2, 3, 4, 1, 2, 3 is our center. The a squared term was first. Therefore, this is horizontal. So we're going to count to the left and the right 3 this time. 1, 2, 3. 1, 2, 3. So the a values are horizontal here. For b, we're going to go the other direction. So we'll go up and down 2. And then for the foci, we'll go to the center and we'll go 2 and a little bit to the left and 2 and a little bit more to the right. And those are the foci, and then connect the outer points for the ellipse. Okay, so the vertices are going to be the endpoints of the major axis, the longer axis. So we have the points -1, 3 and -7, 3. There's a -1, 3 and -7, 3. The co-vertices will be at -4, 5 and -4, 1. The foci, these are a tiny bit trickier in that, first of all, I know that both of their y values are 3, so let me just go ahead and jot that part down. But for the x values, the center is at -4, and the value for c is about 2.24. So if we're at -4, we go to the left 2.24, that'll be at -6.24. And then if we go to the right 2.24, we'd be adding 2.24 back to the -4, so then we'd have -1.76. The length of the major axis is always 2 times A. A was 3, so the length of the major axis is 6. Length of the minor is always 2 times B. The minor, the value for B was 2, so 2 times 2 we get 4. E is C over A. So C was the square root of 5. A was 3, and when you evaluate that, that's about 0.75. For the lines of symmetry, for the vertical, we'll have x equals -4, and for the horizontal, y equals 3. Let's look at 2 more kind of problems. Find the constant sum for an ellipse with foci at -3, 0, and 3, 0, and a point on the ellipse at 0, 4. So the constant sum, that formula is just L1 plus L2 will give you that constant sum of L. Let's flip back to one of the ellipse diagrams so I can show you what that is. Okay, so if we're looking at this horizontal one here, and I'll just erase these other lines. If we have, say we pick any point here, right there, and we connect the foci each to that point. Not a very good job. Oh well. So between the center and foci. So the measurement between the focus and that point would be L1 plus L2. Well, it turns out that no matter which point we pick, so say I pick this one right here, and I add together the length of the distance from each focus again, that those two measurements would always be the same, even if I picked one over here. And all of that ties back in to the set definition, which was the sum of the distances between xy, so if this is a point xy, or if this was a point xy, or even this was the point xy, messy, that says xy. It doesn't matter. Anytime I add together this L1, L2 for any given point, it will always be equal. It's a constant. So that's why we call the constant sum. So going back to our example, the constant sum, L1 plus L2 equals L. So for an ellipse with foci at -3, 0, and 3, 0. So let's just go ahead and draw a picture. So we have the point -3, 0, +3, 0, and a point on the ellipse is at 0, 4. So these are the foci. So remember, that's not what the outside edge of the ellipse goes through. The foci will never have anything going through it. But we can figure out that the center right here is at 0, 0 if you wanted to. But the constant sum will be if we draw in from each side, if this is L1 and this is L2. So we know that, we know the Pythagorean theorem is what I'm trying to get to here, because you can see there's clearly two right triangles, right? If I draw those in, here's a right triangle, and here's a right triangle. If this is 0, 0, then this side has a length of 3, so does this one. Vertically, that has a length of 4 for either one. Well, this would be a 3, 4, 5 triangle. Or you could use the Pythagorean theorem, a squared plus b squared equals c squared. So the outside edge, we have a 5, so that could be L1. This one could be L2. So the constant sum would be 5 plus 5. So that constant sum is 10. And that's what we were looking for right there. So again, I just plotted the points, figured out the distance between the foci and the given point for each one. Here they happen to be symmetrical. So the outside edge was 5. Constant sum would be those two added together. and then 5 plus 5, you get 10. Okay, and then this last problem, I would like for you to do it on your paper, and we will go over it together in class. Hope you have a great day and a great evening, and I will see you later. Bye.